All right, I think we can get started. So welcome back, everyone. My name is Matthias Punk. I'm from LMU Munich, and together with Johannes Knolle from TU Munich, we're going to moderate this session this afternoon. Our first speaker today is Fabian Grusdt from LMU here in Munich. Let me just briefly introduce him. Fabian graduated from Kaiserslautern in 2015 and then moved to Harvard University for 3 years as a Moore postdoctoral fellow. After that, he was at TU Munich for a short while, and since last year, he's a junior group leader, actually funded by MCQSD at LMU Munich. His research, or one important part of his research, revolves around using ideas or the toolbox from ultra-cold atoms to study effects of strong correlations in many-body systems. So without further ado, let me hand over to Fabian. We're very much looking forward to your talk. Can you unmute yourself?
Now you can hear me, right?
Yes.
Perfect. Yeah, thanks a lot for the introduction, and thanks for the organizers for inviting me. It's a pleasure to talk about the research here. And let me start out by thanking my collaborators. Let's see the slides. Yes, so what I'm going to show you is part from collaborations with the Munich group of Emanuel Bloch, and also the experiment in Markus Kreiner's group in Harvard, and theory collaborations from my time in TU with Michi Knapp, and also some work with Lode Pollitt. He will talk later about some other things also. And Annabelle Bott did lots of work on lots of the calculations I will present. Okay, so let me start with the motivation. Much of our field actually originated from quantum optics, and the whole philosophy of quantum optics is really, and for a long time, was to control and understand the individual pieces of physics, that is individual atoms, individual photons, and so on. But of course, nowadays we are in a completely new level where we have gained so much control over these systems that we can put them back together in a very well-controlled way and study many-body effects in these different settings. Examples are correlated bosons. Of course, the BEC set the stage and started the whole field, but now quantum magnetism has become an active field of research. That's also what I'm going to focus on, strongly correlated materials. What I'm going to do, or what I do in my research, is basically to apply the same philosophy from quantum optics again and focus on the individual pieces. And so the idea is to look at these very strongly correlated many-body systems, quantum magnets, and search for the emergent constituents that then in the end describe these very exotic and rich many-body physics that emerge. And so here you can already see some sketches of these should be quarks. And that's in fact another new angle that plays a role here, namely the idea that some emergent particles like these quarks in high energy physics emerge. And so this connection between high energy physics and strongly correlated quantum matter, that's a new, basically a topic that we focus on here. And in fact, I should say this is not really new. Shortly following the discovery of strongly correlated materials and high-density superconductivity, there was a dream that, maybe we can look into these quantum magnets and find the analogs of quarks even in these solid state systems. So far, there have not been very many smoking gun signatures, I should say. But I think, first of all, cold atom experiments and quantum simulators are very well suited to study precisely this problem. And I will, in this talk, present you some results that I believe really hint to the existence of these new emergent constituents, the analogs of quarks, really, in these strongly correlated materials. Okay, so the actual model I will talk about is always the Fermi-Hubbard model. You have fermions with two spins, red and blue, in the sketch, and when they're on the same side, they interact with strong Hubbard interactions. These can be simulated with ultra-cold atoms. And in this theory talk, I will focus on this the large Hubbard U limit, which basically allows me to look at the TJ model. That means we have no double occupancies. And in the end, we basically have to deal with an interplay of hole hopping T. So this is sketched here. The holes in the system can tunnel around. And there's a slower time scale J, the super exchange energy. And this really exchanges two spins on neighboring sites. So these are the two competing processes that are believed to underlie the rich and exotic physics of high TC superconductivity. Okay, so how should any partons emerge, the analogs of quarks? So the starting point is really to formally write the electron or the fermion operators with position and spin indices as a combination of a spinless chargon and a spinful spinon here. And really think of this electron as being composed of these two constituents. In a sketch, the easiest way to look at this is in 1D. And I want to briefly bring up this sketch from Mim's talk again. She showed this morning. For those of you who haven't been there, the idea was they, in Emanuel Bloch's lab, they basically created Hubbard chains in 1D, and then they shot out at time 0 one of the fermions with a spin and a charge. And they saw that a domain wall propagated independently of this charge in this 1D system. And the domain wall is then the spinon, that's one of these partons that only carries spin but no charge. And this chargon is the other constituent that carries no spin but only the charge. All right, and so the first thing I want to mention in connection with this experiment is actually an extension that we proposed a while ago, which is not to shoot out this single electron or the single fermion on this lattice site, destructively, but rather to coherently couple it into an initially empty chain. So the idea is, imagine you have two chains, one is full, the other is empty, and you basically drive this transition here coherently. You also create this type of hold effect. But it turns out if you then do time of flight spectroscopy and image the final spin state in this empty chain, initially empty chain, the response you get as a function of momentum and frequency is actually the ARPES signal. So this is a spectroscopic way of probing these many-body systems. And that, of course, brings us also very much closer to high-energy physics, where spectroscopic probes are more natural. Now, we can look at what happens in this 1D system that's best understood, which is very close to this ideal scenario where spin and charge really factorize into these emergent constituents. The key point here to understand what's going on is that the wave function in these 1D systems is a product of this chargon times the spinon. The product form is very well satisfied because of the spin-charge separation that kicks in. That's exactly to say that the spin and this charge, they do their separate things independently of each other. And now, if the wave function you have is a product, it means if you calculate the spectral response function or the Green's function in your system, you basically have to Fourier transform to get into K and frequency space. And that means you get a convolution because you start out with a product. So here the convolution is written down in full with these integrals. But what this actually means is that if you look at the ARPES spectra you get, they're very easy to understand. And so this is a particular ARPES spectrum for more or less realistic experimental conditions, 16 sites, temperature 0.2 J. That's a little bit cold compared to what they have right now in cold atoms, but should be feasible at some point. And so what you can see in the spectrum is two branches. And I indicated them with these lines. So you can see this first branch here, that would be what we would call the chargon branch. So this corresponds to the single chargon moving around. It has this 2t cosine kx dispersion. But in addition, you also see these lines. So this is one line, there's another one right under here, and you can see it's a whole collection of lines. I just indicated two of them. And you can see that actually these map out a Fermi sea of spinons. So this blue line here, it's exactly the same lines. It's turned around because there's a particle hole symmetry going on. But the idea is that these spinons, they form a half-filled Fermi sea. That's our Mie field level description of the system. And you can see that in this part down here, where you initially have spinons, if you kick them out in the ARPES, you also find a signal. But then if you cross over here, you don't see any signal anymore. It turns out it reappears if you increase temperature or so. So, there are actually states, but they have zero spectral weight simply because they're not occupied at this point. Okay, so with this, I want to turn to 2D and really ask, can we see and find the same type of constituents in 2D materials? What's clear, of course, from the start is that they would be more strongly or at all interacting, so much more complicated. And the regime that seems most promising to search for them is low doping. And for simplicity, to do some theory calculations, we will focus here on a very low doping. In fact, basically one dopant, at zero temperature in theory, or experiments I will show at also, low doping and some elevated temperature. All right. So I want to start out by doing the exact same type of experiment, at least in our heads, as a thought experiment, as in 1D. So imagine you start with a 2D antiferromagnet and you basically shoot out a single hole. So psi 0 is the antiferromagnet. You kick out one of the fermions with a spin. Now, of course, what you would expect if you now time evolve it, you would expect that this charge moves away. Remember, the charge dynamics is faster than the spin dynamics. And so then something is going to happen. So it turns out we can still describe this because T is bigger than J. We can still make it one Oppenheimer type product ansatz. So psi of T is still psi sigma now. That's basically a wave function of a string that's connected to this spin defect that you create. So the picture is that the spinon and the chargon are connected by a string of these displaced strings. You can see here these basically defects that you create. And then if we assume such type of wave function, we can make a guess what the dynamics would look like. And so at time 0, of course, we have a localized spinon and chargon pair. They're both at the same site. So spin and charge still coincide when we kick out one of these original fermions. But then as we evolve, tunneling is much faster than, or quite a bit faster than the spin exchange. That means initially it looks almost as if there was spin-charge separation. So the chargon just ballistically expands. But then eventually on the order 1/j time scale, the chargon will actually realize that it's interacting. So you do create these defects. That means the chargon will be bound to the spinon. That's going to happen at some time of the order of 1/j. And at this point, you basically, what happens is that the system has formed a new bound state of this chargon and the spinon, or sometimes also called the magnetic polaron. And after that, one would expect that this spinon would ballistically expand at long times. Basically, this bound state, the entire bound state would ballistically expand. So just by looking at this and from our parton picture in mind, we see that there should be some interesting multi-stage dynamics. And sure enough, this is what we see. So this is a time-dependent DMRG simulation that we did in this collaboration. And what we plot is the average Manhattan distance as a function of time. And you can see that indeed at first, at short times, there's an initially free expansion of this chargon as we expected it. But then we see there's this plateau-like feature forming. So that's when the spinon and the chargon start to interact. And then at long times, we have the slow ballistic expansion of this whole bound state as it is. The beauty is we can actually compare this to a simple model of this pair of the spinon and the chargon bound by the string. And I'll talk a little bit more about that in a bit. But you can see that this simple model, GST stands for this geometric string theory, actually predicts even quantitatively fairly accurately what's happening here. It gets the slope right. And so that means we have a very good understanding of this dynamics. In fact, there was recently an experiment in Markus Kreiner's group in Harvard. So we, in a collaboration with them, they experimentally did this precise experiment. So they initially pinned a single site. There was an extra potential on there, and then they released the site, which basically means they basically released this hole that they created in the beginning and let it evolve dynamically. And then as a function of the time after the release, they look at the root mean square distance of this extra charge, this hole basically from the center. And indeed, you can see that they see this fast initial ballistic spreading. That's sort of a remnant of spin charge separation. Then it kicks in that they see that the charge is really slowed down. There's interactions. That's because this is a 2D system. And then at long times, you can see that there's a very slow expansion. Hard to tell if it's ballistic or diffusive at this point, but you can see that there's a dependence of the slope here on the ratio of U/T. So blue and green are different U/T ratios, and this means different super exchange couplings. And as expected for the smaller super exchange, that the larger U, the green one, the expansion is slower. And in fact, if you go and plot the same data in this inset here in units of J, you can see that the green and the blue long time expansion, at least they're consistent with actually following the same slope, and that's exactly the slope one would expect from this magnetic polaron picture. So from this, we can conclude that basically the effect has been seen. All right. Of course, we would like to move on and understand in even more detail the structure of these emergent constituents. So, if there's this bound state of spinons and chargens, how can we prove what the structure is and so on? And so now I will focus first on equilibrium situations of these guys. And there are two things one can look at, actually many, but the two I want to highlight here is one is higher order correlation functions. So now quantum gas microscopes are actually able to look at arbitrary order correlation functions. So this is going way beyond what has previously been studied in the traditional condensed matter setting. And it's actually able to reveal in more detail what's going on. Or one can even go beyond just going a few orders up. One can analyze entire patterns and search for strings of these defects that I sort of sketched before. All right. So first of all, let me give you one slide to summarize, and this is really just a broad overview of the theoretical description that we give of the microscopic structure of these meson-like bound states. So the idea is we have that the tunneling is much bigger than J. That's the regime we focus on. And such a separation of timescales actually allows us to describe these mesons in a Born-Oppenheimer way, much like in atomic physics. And so the idea is to write down the ground state wave function as a product of this fast chargon. And sigma here stands for string. And that's because the antiferromagnetic spin environment actually effectively modifies the Hilbert space seen by this fluctuating charge. So the idea is when it goes one way or the other, these two ways are often, most of the time, actually distinguishable. And that's because they leave different patterns of spins behind. And that means when we describe this chargon wave function, we actually think of a single chargon hopping from this, starting at the same position as the spinon, but then hopping on the sides of an effective beta lattice. And that means the quantum states in our Hilbert space are actually labeled by the string configurations. They're exponentially many. And of course, the longer the string is, the more bonds you actually mess up. And therefore, we expect a confining potential that should be linear in the string length. So this is really assuming that the spinon is fully static, as you would do in a Born-Oppenheimer approximation. You put the heavy particle in the center, fix it. So the next thing you would want to do is, of course, you want to describe the slow spinon wave function as well. And in a third step, you can even modify the background, the antiferromagnetic background. So, so far, I assume we just have this antiferromagnetic spin background. But of course, we know that when we dope the system, that can actually change the spin background. So that's sort of a third stage. And so this is definitely true that what we do here is we step by step describe in more and more detail how these bound states look like. Now, the first level theory we do is this FSA, so it stands for frozen spin approximation. We completely freeze the spin background. We also freeze the spinon and don't allow the spinon to move at all. And we just start from an undoped spin wave function. But then we include these string fluctuations of the chargons, and thereby we already include very many spin charge and very strong spin charge correlations. The second stage would be to add even spinon dynamics. So we also allow this spinon to move, and that would give rise to this ballistic expansion that we saw in the DMRG simulations. And in the third stage, that's what we're working on right now, focusing a lot on is what's the effect of dopants on the spin background. But I'm not going to say much about what we found out there. All right. So that's our theory. To give you an idea, first thing we look at is what's the shape of the magnetic polaron cloud. So this is basically looking at a diagonal spin correlator at different distances d from the hole, the one hole that we create. And you can see that here that the DMRG simulations in the ground state that we do, these gray lines, they're very well described by the theory, both first level and second level theory. We can go also to nearest neighbor bonds, again, as a function of this bond distance from the hole. And there you can see there are some deviations here for this first level theory, but it's remarkable how well we can describe precisely the nature of the stressing cloud. In fact, we can go one step further, and that's these higher order correlators. And so the idea is if you just pin this hole and there's no motion, you would expect in an antiferromagnet that all the spins around the hole should be lined. And so when we calculate n hole SC around, actually much like in a Gauss law, in this case the Z2, because the spins just have plus and minus values, you would expect a positive value here. But on the other hand, when the hole is allowed to move and actually move a lot, we would expect it to form or to be at the end of one of these geometric strings of displaced spins, and there one of these 4 spins should be actually from the other sublattice, and therefore this correlator should be negative. And so what again, we looked at the ground state in DMRG and looked at the ground state as a function of the ratio of tunneling in J. And indeed, you can see that these bare or connected, doesn't matter, the blue and red correlators, they are both strongly negative. They're very well described by this first level frozen spin approximation theory here. That's this blue band you can see. And in fact, if you compare this to these yellow curves, so the yellow, that's the disconnected lower order correlators, you can see that not only are these Gauss laws there and negative here for these dopants, for these mobile dopants, but in fact, these higher order, 5th order correlations are actually even much larger than the lower order correlations. And this is very significant, we believe, because you always want to find the most important dominant correlations. That's what you should base your theory on. And if second order correlations here and these disconnected parts are weak, that means that any simple mean field theory would actually have a very hard time capturing the physics of these bound states. Okay. So next we can look, we even take this one step further, look at patterns. And what one can do, of course, is motivated by quantum glass microscopes, look at individual snapshots. So a snapshot could be like this. There's a hole here and there's a certain spin configuration around. That's precisely the type of measurement that's taken in the quantum glass microscope. And what we do is we take snapshots like these, we generate them from theory data, of course, and subtract the perfect Néel state to basically find which spins are not aligned the way they should be in a perfect Néel state. And so that would be indicated here. So we can look at these, that's what we define as a string pattern, and then we can look at the properties like the length of this string, for example. So this is a plot of the string length histogram. You can see that that would be the reference state. That's when we just have a localized hole. We just take the antiferromagnet, create one hole. There's already a broad background, and that's basically because the quantum antiferromagnet is not a perfect Néel state, so there's some noise already. But the significant part is that if we put in strings by hand, so this is again our theory prediction by this frozen spin approximation, we expect a much strongly decreased signal at short strings here and a much broader tail. And in fact, this agrees extremely well again with ground state DMRG predictions for these same types of patterns. So you can see these data points here, they're pretty much on top of our prediction. Okay, so we actually did the same analysis also in this dynamics experiment and took snapshots at each instance of time and looked at the average length of these string patterns. And you can see initially these blue dots here, they rise exactly like this charge-on expands, but at longer times they settle and they don't rise anymore. And this really proves this point that at short times this new mesonic particle is forming, this bound state is forming, but then it has formed somewhere here. And once it has formed, it basically retains its internal structure as it is, more or less. But it's really only the center of mass of this entire object that's moving up here. And again, this frozen spin approximation prediction is fairly close. Maybe there's some decay here due to coupling to magnons, which leads to loss. That's something we didn't take into account. Okay, and then let me get to the last part of the talk and get back to spectra again. And that, of course, makes a much closer connection with high energy physics when one would look for spectral lines and try to analyze those. And originally, of course, this is where high energy physicists have found the first signatures for quarks and basically saying that the structure of mesons, which they thought of as new elementary particles at first, but then they could explain them as really composites. So we want to do the same thing and look at spectra. And here again, the key message is that because of the separation of timescales, we can make a Born-Oppenheimer ansatz and describe our wave function as a product of a string part here, where the charge-on is bound to this slow spinon times the spinon part of the wave function. And again, exactly as in 1D, because this is a product wave function, the spectral function you would get would be a convolution of the spinon and the charge-on part. So formally, it looks very much the same as in 1D. But there's one important difference, which is that the string is now, or the charge on the string is now actually bound to the spinon. That's because of this linear string tension that we have. And as a result, we expect this part to have discrete spectral lines separated by gaps due to vibrational and rotational excitations. And one can actually check that this leads to some universal quasi-particle residue dependence on this ratio J/T. So we went ahead, looked at the quasi-particle weight Z in the ground state at momentum pi half is a function of J/T here. And you can see that this new DMRG simulation that we did here, these red points, they're very consistent with earlier quantum Monte Carlo simulations here, but they also match perfectly this gray line. And this gray line is a semi-analytical prediction by this, just a simple beta lattice calculation, much simpler than beta ansatz actually. And so you can see this perfect agreement really demonstrates that we have very good microscopic understanding of these ground states now that form in these systems. We can go one step further and look at the K dependence. And the idea is, if you have the Born-Oppenheimer ansatz, the spinon has a mass that's inverse of J, and therefore it's much heavier than the slight inverse of T mass of these charge-ons. And as a result, you would expect that all the center of mass dependence, the dispersion relation of this bound state, should be entirely determined by the spinon. And that means if we have one excited state here of this charge-on, it should be just parallel in K-space to the ground state, because both share the same spinon dispersion. And indeed, you know, this is the spectral function that calculated from this time-dependent DMRG, and you can see there's the ground state here, the lowest band, and much in parallel you can see there's this first excited band, and it has the same qualitative shape, has some gap here, and so this is really basically you know, very much consistent with this idea that spinons and charge-ons form a bound state. Turns out one can look at the gap, and if the interaction between the charge-on and the spinon is linear in the string length, there would be universal scaling with T to the 1/3 times J to the 2/3. That's been known actually for quite a while, but we confirmed it again in these simulations here. So we extract this gap here precisely at the nodal point in the ground state. And you can see if we plot this gap as a function of J/T to the 2/3, these red DMRG data points that we have fall into a perfect line. So this really indicates that this power law here is there. We can also see this analytic geometric string prediction in gray matches extremely well without fit parameters the numerical results, and everything is also consistent with QMC, earlier QMC results and in this strong coupling regime. At somewhat weaker couplings, we believe that this QMC, which required some analytic continuation, probably didn't resolve all the details there. And so looked at slightly different peaks, which is what we believe gives rise to this slight mismatch in this regime. Okay, lastly, one can look at the K-dependence of quasi-particle weight or the dispersion relation. Let me just mention that again, you know, there's a strong dependence on K and this time-dependent MPS. Here, this red data follows the green expectation from a second-level trial wave function that we tried. So, you know, that just basically tells us that we really understand in great detail the properties of these quasi-particles that we have there. Okay, I think my time is pretty much up. The outlook for these upper spectra is, you know, if we ask what do we really need to have smoking gun signatures to be able to say that something like quarks exists even in strongly correlated materials, what we want to have is even more resonance. So we're looking for this. We are thinking maybe these small additional features that we see here, maybe something interesting, maybe related to some other resonances. So that's future stuff to come. And with this, so I want to skip this part of the talk and come to the summary and outlook. So the key message is that these bound states of spinons and charge-ons here, we can understand from a simple picture where spinons have a very heavy mass, 1/J. We have charge-ons with a very light mass that allows one to do Born-Oppenheimer type of ansatz, and then gives rise to an analogy between you know, strongly correlated systems and these mesons here, and atomic physics where we have a heavy nucleus and a light electron dressing it up. And finally, the photons, those would be not you know, number conserved particles. We think the magnons may take a similar role. We haven't really fully looked into this yet, but it opens up a very new perspective on you know, drawing even deeper analogies between standard AMO physics and AMO techniques that we want to apply now to these strongly correlated electron systems. So with this, I want to thank you and happy to take questions.
All right, thank you, Fabian. Thanks very much for this interesting talk. I'll pass over to Johannes for the Q&A.
Yes, thank you very much. So let me first tell the audience, so you can post the questions via the link on the Mentimeter. And so the first question is, let me just read it out aloud. There are two at the moment. At finite temperatures, as an actual experimental situation, spin fluctuations as well as double and Holland fluctuations will be prevalent. Would you comment on the finite T effect on your theory, please?
Okay, of course, that's true. How many double and Hole fluctuations you have depends on the ratio of temperature over U. Luckily, the temperature is way below the Hubbard U, so probably thermal double and Hole fluctuations are not so important. We know that quantum fluctuations, and double and Hole pairs do play a role. So this is all based, what we do is based on this TJ model. Experimentally, there's a chance that one could ramp up lattices in precisely such a way to image without these quantum fluctuations. That's an interesting future direction. In general, it basically reduces correlators that we have, and one has to be careful with the data analysis, but these double and Hole fluctuations would not destroy things. Now, with regard to temperature, not on double and Hole fluctuations, but in general, at low temperatures, everything should be fine. So you saw that there's this vibrational gap to the first vibrational state of the ground state. That would mean that as long as temperature is below this vibrational gap, everything is fine. It's much more interesting when the temperature is comparable to this vibrational gap. We believe there are some rotational excitations. Their number can be large, and so around temperature equal to J, we think that very interesting non-trivial effects can happen. I don't want to go in more details now.
Okay, so then maybe a brief last question because of the timing. So the question would be, could the meson in principle exchange angular momentum with its environment? Well, I guess if you want to do neutron scattering. Yeah.
Yes, that's a very excellent question. Of course, we are on a lattice, so angular momentum would have to be quantized in discrete, C4 rotational symmetry. That would totally work. I mean, total C4 angular momentum has to be conserved then, but that's the total conservation. Oh, yeah, that's an interesting question to look at for sure.
Okay, okay. Good. So then other questions, they can be later on then in the roundtable discussion be asked with the speaker. Yes, so I guess we will continue with the next talk.